Good morning and welcome to the general meeting of the Cost Action Fundamental Challenges in Theoretical Physics. Please welcome Professor Fabio Zwirner, Vice Rector for Research at the University of Padua.
Good morning and a warm welcome to all of you, also on behalf of our rector, Professor Daniela Mappelli, as participants in this kick-off meeting of the Cost Action Fundamental Challenges in Theoretical Physics hosted by our mathematics department. Although I see a number of familiar faces in the audience, all those who are not so far from my age, I'm very glad to see that there are many young participants. Some of them may not have been in Padua before, so I would like to say a few words to introduce our university to them. Padua University was founded in 1222, more than 800 years ago, and its motto is Universa Universis Patavina Libertas, which means universal freedom for all in Padua. And we are trying to stick to it also in the present times, as you can hear from the noise in the courtyard. Our long history has several highlights connected with physics and mathematics. For example, Nicolaus Copernicus was a visiting scholar at the beginning of 1500, and Galileo Galilei, almost a century later, spent 18 years in Padua, which he later described as the best years in his life. Professor Chiarellotto, who will speak after me, will mention more examples from mathematics. Today, the University of Padua has about 70,000 students and 2,000 PhD students, more than 2,700 professors and researchers, as almost 100 postdocs. It's a large university spanning most of the disciplines in physical sciences and engineering, life sciences, and social sciences and humanities. And it's organized in 32 departments and 27 research centers with one university hospital, one veterinary hospital, one experimental farm. It is also an excellent school called Scuola Galileiana in honor of Galileo, who just celebrated a few days ago in this room its 20th anniversary. Coming to research, our budget for new projects is roughly 70 million euros a year, 1/3 of which come from internal funding and 2/3 from external funding, national and international, mostly European. And in terms of European funding, we are the best performing Italian university in Pillar 1 of Horizon Europe, with 70 Marie Sklodowska-Curie fellowships and 24 ERC grants so far. And we are doing well also in the other two pillars. We have also a good tradition in international networking. We are member of two university alliances, Coimbra and Arcus, and more specifically, we are active as today in research networking through the Cost Actions. So far, we have been participating in the 130 Cost Actions. We have been chairing 4 of them, one in biology, one in health sciences, one in bioinformatics, and last but not the least, the theory challenges that is meeting here today. Apologies, I regret I will need to leave you soon because of other commitment, but I will be back this afternoon. For now, I congratulate Professor Sfondrini and all those who contributed to the organization of this event, and I wish you a very successful kick-off meeting and a pleasant stay in Padua during these 3 days. Thank you.
Thank you, Professor Zwirner. Please welcome Professor Bruno Chiarellotto, Director of the Department of Mathematics, which hosts the cost action.
Good morning, everybody. Dear colleague, dear participants, to this starting meeting of the cost action of fundamental challenges in theoretical physics. It's a pleasure to welcome you in this Aula Magna. I would like to say that there are two accidents today for me. First of all, that I wear a tie. I'm not so used to have this tie and during a conference. And I think that you understand this. The second accident is the fact that it's me, that and my department is hosting the cost action. It would have been the same if instead of me here, you would see the head of the math department of physics. And this is, I think, the basis of the cost action. As you know, this cost action means to cross-border research, interaction, cooperation, and as I see now, you are from all over Europe and abroad. So this is really the basis. This is true also at the local level, at the level of Padova University, because there are several researchers working on this action, starting from Professor Sfrondrini, which is not in my department, by the way. So it's, even if math department is the host of this action, the chair actor is not in our department. This is true at the local level, but it is also true at the global level. You are from all Europe and abroad, and is really, really the basis of this action. But I think there is a deeper meaning in having the first meeting of this action here in Padova. It is enough to think about the name of the math department here in Padova. The name is Dipartimento di Matematica Tullio Levi Civita. Levi Civita was a colleague, he was a professor. I am here now. So he was here, and before him, his mentor, Ricci Curbastro, both of them, they were professor here. And I'm thinking that they were teaching here, or perhaps in another room close to us. That's wonderful. And this is the beginning. And I like to think also, in connection with this cost action, I like to think about the visit of Einstein here in Padova. He visited Italy, and he wanted to meet Levi Civita. Not only because they had really deep collaboration before and fruitful, as you may know, but he wanted to meet him in person. And this, I think, is really important. I like to have collaborators. I think that you like to have collaborators, but sometimes it's so nice to spend the time together to discuss, not just during the conference, but perhaps in the middle between two talks and so on. So I think that's really important that we are all here. So I think that it's normal to have the first meeting of this cost action here in Padova. Einstein, Tullio Levi Civita, Ricci Curbastro. So I think that I like to think this cost action as a continuation of this Einstein visit to Padova and to Italy. So I wish a wonderful action and with a lot of collaboration. And I wish to the network the best with a lot of theorems and results. Thank you very much.
Thank you, Professor Chiarellotto. Please welcome the Cost Action Chair, Professor Alessandro Sfondrini, who will be chairing today's session of the meeting.
Thank you very much. I wanted to thank Fabio and Bruno for their very nice words. I will have more announcements throughout the day about many practicalities, also about unforeseeable circumstances that happened today. But for now, I think we are all eager to get on with our scientific program, so I would like to welcome Jan de Boer, please.
Okay. Well, this is a spectacular setting to give a talk. I don't think I ever had so much space to walk around ever. When usually you're in a small little but now I can just wander about while I'm speaking, which is always a good thing. So the instructions that Alessandro sent were to give a vision talk, but his explanation was that it should be basically an invitation to work on certain problems. So I was thinking whether to isolate one particular interesting problem or whether to sort of just write some thoughts on slides. And since it's the first vision talk, I did not literally follow those instructions, so I just wrote some thoughts that I had about the subject on some slides with the hope of maybe generating some discussion, because it's always nice to have some discussion at these meetings. Let's see. The clicker, where am I supposed to point in a particular direction, or? Yep, thanks. So clearly one of the most important challenges of theoretical physics is to understand the nature of quantum gravity. And therefore I thought I'd try to write down a few things that I think we have learned so far about quantum gravity from string theory, and a few things that maybe we have not quite learned yet. And by all means, it's also an invitation to disagree with everything that I said. So because I might say something and you might strongly disagree, and by all means, raise your hand and let's talk about it. But one of the main promises of string theory was that it provides us with a theory of quantum gravity. And I think there has been obviously a lot of progress, mostly in the context of ADS-CFT. So there has been a lot of progress in understanding black hole entropy as really corresponding to the counting of a certain set of degrees of freedom, both for BPS black holes and to a lesser extent for non-BPS black holes. So I think it's beyond reasonable doubt that black holes in string theory are just, that the entropy of a black hole in string theory is really counting microscopic degrees of freedom. There has been a lot of progress in understanding the relationship between black hole formation and thermalization, understanding the chaotic nature of black holes, understanding how they scramble information. There has been an amazing amount of work in trying to connect concepts of quantum information theory to quantum gravity results, which always raises the question that I did not write down, is whether we should try to maybe eventually reformulate gravitational theories in purely information theoretic terms, because it's such a powerful language and it has so many important applications. I also think, and this is maybe something that people might disagree with, is that the information paradox has been dealt with satisfactorily by now. I think that's done. However, there are definitely several issues that maybe remain somewhat unsatisfactory. But I would also like to ask the question, where I don't have the answer to any of these questions, but I would like to ask the question, what is the best we can hope for? Because if a quantum gravitational theory, at least to the extent that we understand it in ADS-CFT, if you're in the quantum gravitational regime, for example, when you create a black hole or you're doing something else, you're in the regime of the dual field theory, where physics is very strongly coupled. It's a large N theory, and it's a very chaotic system. So it's not an exactly solvable system, it's not an integrable system, it's a messy, chaotic system. Now, typically we do not have any hope to explicitly solve such systems. Like if you want to solve a strongly interacting quantum many-body system and it has 10 to the 26 particles or something, we are not going to solve those equations. So you may ask what actually is the best we can hope for, given the fact that this is a strongly interacting, very chaotic system. And maybe one answer is that the best possible answer is maybe general relativity with a bit more than that, because that's some sort of, if you wish, hydrodynamic description of this very chaotic system. But if someone has a great idea and is convinced that there is much more to be said about these strongly coupled chaotic systems than what we can do right now, then please let me know. Yeah, so one interesting little, this is maybe the most little technical thing that I'd like to encourage people to think about, is that there has also been a lot of progress in this quantum gravitational context to think about the so-called factorization puzzle and the meaning of wormholes. Wormholes are solutions of the Euclidean field equations with more than one ADS boundary, and alpha vacuum and so on. And I think, again, conceptually, it is by now pretty clear what the right interpretation of wormholes is. They correspond to correlations that arise in the system that arise because a gravitational theory always does a certain amount of coarse graining. If you coarse grain a theory, it becomes a slightly statistical theory, and statistical theories have correlations in them, and these wormholes are just a geometric representation of the correlations that are due to this coarse graining procedure. However, these correlations are not fundamental. They arise as an artifact of the low energy coarse graining procedure. Now, if you take, however, one part of this discussion is incomplete and unsatisfactory, I think. That has to do with the following. So if you coarse grain a high energy sector of a theory, then the spectrum in these high energy sectors of the theory is presumably described by random matrix theory, because that's the universal description of the spectrum of any chaotic, strongly coupled chaotic quantum system. If you want to see the correlations in random matrix theory, so in random matrix theory, different parts of the spectra are correlated to each other, and you can also try to compute those correlations with suitable wormhole-like computations. However, it turns out that the relevant wormholes that you need to write down in order to see those semi-classical, if you wish, correlations in the spectrum are off-shell. So some of the statistics of the theory can be diagnosed with a gravitational theory, but you need to take the theory to be slightly off-shell. And that's a very weird thing, because normally a semi-classical theory is defined as a sum over saddle points. Then in each saddle point we do some loop computations and so on. And we usually don't try to do anything properly off-shell in a low energy effective field theory. But here, if you want to see these correlations, and there's many reasons to believe that these computations are consistent and give us the right answer, we have to do computations that are slightly off-shell. Now, there is a context in physics where we do slightly off-shell computations. For example, if one does so-called constrained instanton computations. But again, I think the theoretical framework that explains exactly when this is allowed and in what sense this is a good approximation to anything is something that we don't fully understand. So I think there's something interesting to be learned from studying the precise rules of the game that explain how to deal with slightly off-shell computations in a semi-classical gravitational theory. Another thing that I think is not quite as well established as it should be has to do with the fate of the infalling observer. If you want, in principle, we would like to do the following computation in ADS-CFT. You give me any state in the CFT, and I am going to predict for you what happens to an observer that moves from the boundary of ADS inward in ADS in that state. That is something that you would like to predict in ADS-CFT. Now, if that state is a high energy state and it describes a black hole or it describes the formation of a black hole, then in particular we would like to explain what happens to an observer to what is going on in the experience of an observer that falls through the horizon of the black hole. Without assuming much, I think many attempts to explain the fate of the infalling observer have a circular argument in them, because you kind of already assume something about the interior, and then you show that maybe that is a self-consistent assumption, but you would like to derive it from the beginning. You would like not to build these things in as some sort of circular argument. And the reason why this is a challenging problem, and I spent several years trying to figure out what the way to do it is, and there's a long, that paper there is the result of 3 years of hard work trying to figure this out, is that it seems very difficult with current technology to unambiguously answer this question. The problem is as follows. So if you have a microscopic state in the field theory that describes a black hole, and you want to unambiguously describe the fate of the infalling observer, from the boundary point of view, what happens is, in boundary and field theory language, is that you basically have a ball of plasma in your boundary theory, which is the dual description of a black hole, and you throw a perturbation at this ball of plasma, and it gets absorbed by the ball of plasma. It's a thermalization process. So from the boundary point of view, what happens is that as this observer approaches the horizon of a black hole, from the boundary point of view, that observer gets thermalized. It becomes part of the thermal bath. And there is a particular time, if you become part of the thermal bath, there is a particular time when you no longer have a simple probe of what went in. So the information of the thing that you threw into this bath gets scrambled all across the bath. And if you then try to probe it with a one-point function or with a simple two-point function, you will not be able to tell that something went into this bath. It will just have thermalized. So from the point of view of simple observables, after a particular moment in time, which normally the time scale we call the scrambling time, after a certain moment of time, from the outside point of view, this observer has just been absorbed by the black hole. And there's nothing there's no trace left. But if you want to reconstruct what goes on once this observer falls through the horizon, you sort of need to still probe later timescales in the problem. And those later timescales in the problem, from the boundary point of view, are very hard to probe, because you threw something in, it got thermalized, and everything got scattered everywhere. Now, pretty much the only theoretical concept that we have that keeps on doing something interesting after the scrambling time is the notion of state complexity. There is a notion of state complexity that basically tells you, given a set of unitaries from an a priori determined list, how easy or difficult it is to go from an initial state to a final state. How many of those unitaries do you need to go from an initial state to a final state? And it's a very detailed quantity, because it depends on the details of your set of unitaries and so on. But regardless of those choices, after the scrambling time, for generic choices, you can argue that the complexity of the state still keeps on increasing. And the result of this many-year exercise was that if you really want to unambiguously try to reconstruct what goes on if you fall through the horizon of a black hole, if you want to do it unambiguously, then presumably you need a notion of complexity of some sort or another. And that's a long story. We tried many non-complexity things, they all failed. So the more general question here is, so one question is a zeroth order question. If you have some initial state and you fall through the horizon, what is the probability that nothing happens? Intuitively, because of the equivalence principle, it would probably say that's 1, because why would anything happen? On the other hand, you could imagine, I don't know if you can see my pointer, that your state is such that basically you created some excitation that flows in and that goes in this direction. So from the southwest to the northeast. And if that would mean that once you cross the horizon, you would hit that excitation. And you would like to, presumably that's a very rare event, and the probability that it happens is very low, but you would like to have a mathematical computation that tells you that in a typical state this typically does not happen. And we do not have such a computation right now. More generally, there's still, I think, an interesting question, more generally, what the role of quantum computation and computational complexity is in these quantum systems. But the thing that's really holding us back is a precise dictionary between a precise bulk quantity and any precise definition of complexity. So far it's a very vague duality where we relate a bulk quantity to something that is morally a complexity quantity, but the precise definition we do not know. And then the last sort of, in this class of questions I would like to ask is, what is the boundary probe of the singularity of the black hole? So we have the question about the infalling observer, but this is also something that I think we haven't really fully answered. You might also wonder whether this is supposed to be a red herring of some sort. But more generally, having a clean criterion in ADS-CFT from the boundary point of view, when the semi-classical description in the bulk breaks down, would be a very nice thing to have. My suspicion is that this has something to do with what you could call a reconstructability problem. Because we're trying to reconstruct semi-classical physics in some region of space-time, and we're trying to make a model of that semi-classical physics in some Hilbert space. In ADS-CFT, it's some sector of the boundary theory. So there should be a map that encodes all that semi-classical physics in a piece of the boundary Hilbert space. Now, as you increase the space-time region, both in time and in space, if you increase the size of the space-time region, and you want to have semi-classical physics being valid everywhere and described everywhere at the same time, then presumably you need a larger and larger Hilbert space to be able to describe all that semi-classical physics. And my suspicion is that there is some interesting relation that tells you that if you have a given region of space-time, that there should be a bound, a lower bound on the dimension of the Hilbert space of states that you need to consistently describe all that semi-classical physics. And I think basically the singularity is nothing more than a sign that by the time that you reach the singularity, the amount of space-time that you're trying to describe in terms of a fixed Hilbert space is just becoming too large. You're running out of Hilbert space. This is why the semi-classical description must break down. And I wouldn't be surprised if there's a similar argument could be made in de Sitter, because there are good reasons to believe that de Sitter space, if it makes sense, as a quantum theory, has a finite dimensional Hilbert space associated to it. And if you want to describe de Sitter space for all and eternity, and every single semi-classical process that could take place in de Sitter space in terms of a finite dimensional Hilbert space, then presumably this is impossible. So maybe the fact that you run out of Hilbert space, or you run out of resources, there might be an interesting connection to what in quantum information theory is called resource theory. The fact that you run out of resources might be a way to understand why certain space-times cannot be self-consistently be described semi-classically for all of time. Oh, not too bad. You give me an angry look, right? Yeah. I'll try to stick in the 25 minutes. Then these were some interesting questions within ADS-CFT. Then I also listed a few questions that are maybe beyond ADS-CFT. The first one is that in a much more general sense, if you look at the work based on scattering amplitudes, bootstrap approaches, the swampland and so on, then one output of all of these computations is that you get bounds on the coefficients of the various terms in the low energy effective action. These cannot be anything, there are bounds on the things that you get in the low energy effective action. And especially if you have a gravitational theory, it roughly seems to be true that higher derivative operators really are Planck suppressed. There's clearly some numbers of order unity there, but there doesn't seem to be a nice way to sort of enhance higher derivative operators. So that's an interesting question, because if you could enhance higher derivative operators, if you put a large number in front of them, then the effect of higher derivative operators would phenomenologically become more important. So from a phenomenological point of view, the fact that we, if you could put these bounds really rigorously on it, I think it's only done with certain assumptions and in certain context, if you could really put rigorous bounds on this, you would also put strong limits on the extent to which we ever are able to hope to see anything quantum gravitational in the cosmos. And maybe the conclusion of all of this is that's super unlikely, because all those higher derivative terms perhaps are just very small and never really relevant. And it will be very important to nail this, because if it's true that higher derivative terms are really not that important ever, that would be an important lesson. It would also be a slightly depressing lesson, because that would make it even harder to see any interesting quantum gravitational signature in the universe. An entirely different way to try to understand quantum gravitational theories is not to do the ADS-CFT game, but to look at different decoupling limits that you can take. And a famous decoupling limit that you can take in M-theory is something where you put M-theory on a circle, a space-like circle, then you take a limit where you make the circle null. You keep the number of momenta that go through that circle fixed. That's a conserved quantum number after all. That's the number n. And then you boost the circle into a null circle. And you can argue that in that limit, it's a very strange limit. It's called discrete light cone quantization, because we have a compact null direction. So you have to be very careful what you mean by that limit. And in some sense, it's also, again, a weird, strongly coupled limit of M-theory. But in that limit, we get a very simple quantum mechanical system. It's called BFSS theory. You may have heard this is an old thing that was invented in 1995, basically. So it has been around for almost 30 years. And it's, in principle, a very simple theory, because you just take n equals 4 super Yang-Mills theory in 4 dimensions, and you dimensionally reduce it down to 1 dimension. And then you have some quantum mechanical theory, and that's BFSS. So in principle, it's a relatively simple theory. It has some fermions, a gauge field, some scalars, but it's notoriously difficult to compute anything. But if you want, there is a super simple dual on paper. You can write down the equation of M-theory in flat space. So it's not ADS, it's flat space. And it would be wonderful to attempt to try to get a bit more out of BFSS. So one interesting thing you can do is you can put BFSS on a computer and you can numerically simulate it at finite temperature, and you can see whether the thermodynamics agrees with the thermodynamics of a black hole in M-theory, and it works. So you can actually do some numerics. But as far as important fundamental questions in quantum gravity go, I think we have so far not been able to employ BFSS very much. And BFSS is part of a much larger class of decoupled theories that all describe different corners of string theory. For example, if you throw in an extra circle in M-theory and you do again this discrete light cone quantization, then we get a 1 + 1 dimensional theory. It's called matrix string theory, which again looks deceivingly simple, but unfortunately we have not been able to very successfully use to do something proper quantum gravitational. What you can see is that you get the spectrum to come out okay, and you can maybe see that type 2 supergravity lives correctly in it, but we have not been able to get much more out of it beyond that. Another observation I wanted to share is that, well, quantum gravity is a non-local theory. And the reason why the information paradox has been resolved is basically, it's basically a breakdown of locality. One formulation of the information paradox is what was the mistake that Hawking made in his computation of Hawking radiation, where he did a semi-classical computation. Well, the mistake, between quotation marks, it's not really a mistake, but the thing that breaks down in the full quantum theory is locality. Because if you do a semi-classical computation of Hawking radiation, but you allow for very tiny non-local effects at all length scales, they should not be confined to a finite size, they have to be on all length scales. But once you allow for non-localities on all length scales, information can come out. And that's the main lesson from all the studies in ADS-CFT. So locality breaks down, and that in particular means that if you have a gravitational theory semi-classically, you cannot take two regions of space-time and factorize the Hilbert space, because it's a non-local theory. You cannot really do that. You can do it in the semi-classical theory approximately, but in the full quantum theory, this does not really make sense. It's still, however, interesting that if you think about ADS-CFT, and you think about the RT surface that computes entanglement entropy, is that somehow there is a very distinguished role for extremal surfaces in ADS-CFT. Because in extremal surfaces are the boundary of what's known as an entanglement wedge, and those are the regions in space-time, so that is this very tiny little green region here. Those are the regions in space-time that can be efficiently reconstructed from a part of the boundary theory, where you do have an approximate factorized piece in the Hilbert space, because it's associated to a spatial region in the boundary. So somehow, locality works almost as well. Locality works as well as it possibly can across extremal surfaces, but not across general surfaces. So apparently there's something important about thinking about the location of extremal surfaces in any gravitational background, because somehow it tells you something interesting about the way the underlying degrees of freedom are organized and entangled with each other. But we don't really understand the rules of the game here very well either. But it's something to, I think, worth thinking about. Another cute, so I just listed some observations. I have one more slide and I'm done, and then you can disagree with me. But, another little observation, I think it's amusing, is that so black holes are believed to be described by typical states or superpositions of typical states. And all typical states, well, almost all typical states are supposed to look like a black hole in practice. But there seems to exist a basis for the black hole Hilbert space of atypical states that at one moment in time look very different from a black hole. If you would then take those states, those will not be energy eigenstates, because if you take those states and you let them run for a little bit of time, they will still collapse and make a black hole, so they're not energy eigenstates. But there is some evidence that there exists such a basis of states. That means that in some sense, at least at one instance of time, you can sort of disentangle the black hole, if you wish, into its individual constituents. That's a remarkable thing. I'm not sure how rigorous we believe that, but there are very good also theoretical reasons to believe that this is possible. And I wonder if this is useful for something or just a weird observation. You might hope that you can learn something about the black hole, but you cannot use it to do any scattering, because the time scale for scattering is much longer than the time scale for collapse of these states. So maybe it's more like a theoretical fun observation rather than something very practical. But you might hope that at least at one moment in time you can sort of disentangle a little bit what the interior structure of the black hole is. You may also have noticed that in the last few years there was a lot of excitement applying methods of algebraic quantum field theory to questions in quantum gravity. I think so far most of those methods are very much limited to semi-classical gravitational computations. At a technical level, what one can do with these von Neumann algebras is try to explain some entropies of black holes and other things that you see in certain spacetimes. Not just ADS, but also in flat space and in de Sitter. By playing games with algebraic quantum field theory in these backgrounds, you can understand some, you can more or less understand some of the entropies that you compute in these backgrounds. But this von Neumann technology so far is not a full quantum gravitational approach to the problem. Because in ADS-CFT, for example, if you take a black hole in ADS-CFT and you apply this von Neumann machinery, you get what's known as a type 3 von Neumann algebra. That's a fairly generic type that you find in quantum field theory, then it's very interesting that if you add an observer to these backgrounds and you combine the starting algebra with a little algebra of the observer, so you add some external degrees of freedom to the system, which in principle is not supposed to be allowed because the observer is part of the system. The observer is not supposed to have some independent God-given Hilbert space. But if you nevertheless take a background and you add an observer and you give that observer some its own little piece of Hilbert space, and you look then at what happens to the algebra, then it changes from a so-called type 3 to a so-called type 2 algebra. And in type 2 algebras you can define things like traces, which in type 3 algebras you cannot. This is why once you add an observer and you can define a trace, then suddenly you can define things like entropy up to some normalization constants and so on, and some other technical details. So that's nice, but the thing I think that's kind of missing in order to make this into a real tool for actual quantum gravitational questions is to go from a type 2 to a type 1 algebra. Because a type 1 algebra, that is literally the algebra of operators that you have in a CFT on a cylinder or on the plane. That's a type 1 algebra. Those are the simplest possible von Neumann algebras. And if we are not going to understand how to go from a type 2 to a type 1 algebra, then this von Neumann algebra approach will have limitations as far as getting actual quantum gravitational lessons from it. It has, for example, although you can compute entropies by taking traces, it has not elucidated really the underlying microscopic degrees of freedom, because those traces, they're not literally the traces over Hilbert space, there's some other trace. I think it's also interesting that there seems to be some advantage of adding external observers to systems. It somehow makes the problem more well defined. And it's easy to understand why, if you, for example, have a closed universe, it's great to have external observers added to it, and why it gives you a lot of technical power. That's simply because in a closed universe we don't have observables. It's very hard to define a good observable, because there's nothing to hold on to. Every point is related to every other point by some diffeomorphism and so on, so you have nothing to hold on to. In ADS-CFT, we have the boundary to hold on to. All observables we define in ADS-CFT are with reference to the boundary. But in other spaces, we don't have these boundaries, and we have nothing to hold on to. But once you add an observer to one of these spacetimes, suddenly there's something to hold on to. You can define an observable with respect to the observer. And that's why suddenly the whole technical machinery becomes much more powerful. But the price that you pay is that you add an external Hilbert space to the system. And on the one hand, it's good, because you all think you're conscious beings, and you all think that you have maybe a Hilbert space in your brain that you can independently manipulate. And maybe that's the kind of Hilbert space that we're talking about here. So it's maybe a good model of consciousness and intelligence and reality and so on. But ultimately, in a closed universe, everything should fit in one big system, you think. Unless, well, in this setting, unless, of course, there is something super, you know, that our mind is not really part of this universe and it's part of a bigger entity, and like over there or so. Another thing that I think is also interesting is ADS-CFT is very powerful because it's a boundary value problem. We have a boundary, it's a conformal boundary, but we have a boundary, and we define a boundary value problem. And you can ask, well, can I not put boundaries anywhere and define other types of interesting gravitational boundary value problems? Because I can put boundaries in other spacetimes, I can put boundaries in flat space, I can put boundaries in de Sitter. Can we not use that to learn something? Yeah, presumably you can learn something, and a lot of work recently has been done. For example, TT bar deformations are believed up to issues that they correspond to moving boundaries inward. A lot of the work on brane worlds and so-called double holography uses branes, end-of-the-world branes, and basically boundaries of space-time. And maybe there's maybe, well, I wouldn't be surprised if we can learn much more from this approach as well. The general drawback is that if you put a finite boundary in space-time, is that the theories on the boundary tend to be non-local. You can already see that in the TT bar example. And that means you have to start to think about non-local dual descriptions of species of space-time. And then clearly, it's all much less powerful because it's all non-local and everything. But clearly it's worth exploring a bit more. And then the last two things I wanted to briefly say is, the first one is that there has been a lot of work recently on something called celestial holography. The work so far is almost void of holography. It's looking at scattering amplitudes in flat space and reinterpreting those amplitudes. It would be nice to put a bit more holography in celestial holography. And the first thing that you might want to do is try to stick a black hole in flat space and see what that means in this language. That's very different from ADS-CFT because a black hole in flat space is unstable. It will evaporate. But maybe a great warm-up exercise is to first go back to ADS-CFT, because if you're well below the ADS curvature radius, you effectively have a piece of flat space as well. And if you put a black hole in that flat space, those are very tiny black holes from the ADS-CFT point of view. I don't think we know the dual description of those black holes in ADS-CFT either. So it might be a nice warm-up exercise in order to try to see what black holes in celestial holography mean, is to rethink what tiny black holes in ADS-CFT actually mean. And the final thought that bothers me is that it is extremely difficult to find weakly coupled de Sitter vacua in string theory. Maybe they don't even exist. So then perhaps we should just stop working on de Sitter, because it's a wrong question to ask. If it's true that there are no weakly coupled de Sitter vacua in string theory, but all cosmological solutions have rolling scalars or other features, then maybe we should try to do holography for all those other solutions and not for empty de Sitter. Maybe it's a misleading question to ask about the holographic dual description of de Sitter. Maybe it's just a misleading question. And the fact that it's so hard to find weakly coupled de Sitter vacua, it feels like the world is trying to tell us something. Because on the one hand, you can make arguments that there should be like billions, and then on the other hand, you can't find a single one. So there's something really strange about the whole situation. So somehow I think there's something here that we're missing. And that would be, I'm not sure what. If I knew, then I would work on it. But I feel like we're missing something important here that we need to think about. So I'm not even sure we're asking the right questions in this context. Certainly we can do scattering amplitudes in de Sitter. You can do quantum field theory in de Sitter. That's all fine. But if you want to do a proper quantum gravitational version of de Sitter, I honestly don't know whether we're asking the right questions. And I'll leave you with that. Thank you.
Thank you, Jan, for posing all these very interesting and challenging questions. Maybe somebody already has answers or comments or more questions. Yes? Or objections?
So thank you for your very nice talk. I'd like to ask about the possibility you mentioned that it is possible to predict the future of the history of an unfolding observer into a black hole from the state in the boundary. But wouldn't that mean that it's possible to obtain information from the black hole interior at the boundary asymptotically? Isn't it strange?
Yes, well, in principle, if you have only one boundary, we do ADS-CFT with one boundary, and we choose a state in the boundary theory that, say, describes a shell of matter that collapses into a black hole, but it's all in one side. And that state and that single theory should know everything about the gravitational interior, in principle, according to ADS-CFT. So in particular, it should also know about the inside of the black hole. That's part of all the information that is possibly available is in that one state, including the interior of the black hole, if it exists. It should all be there. Is that your question, or?
More questions for Jan? Maybe a quick one from myself. About the idea that you can maybe use minimal surfaces to sort of split up the Hilbert space. So in many interesting cases, there are more saddles, so you can actually need to sum over minimal surfaces. Just taking one would not suffice. So what do you think that could tell you already about the impossibility of separating Hilbert spaces?
Yeah, that's good, thanks. Yeah. Yeah, if you ask a question about, say, entanglement entropy or things like that, and we are instructed in principle, then there could be more than one extremal surface. Then normally you take the one that minimizes. Is usually the answer to some minimization problem. But there can be more. But there is interesting information also in these other extremal surfaces. All extremal surfaces, regardless of whether they are computing the entropy for you, they are on some sort of information barrier of some sort. So in that sense, finding them all is still an interesting way, and maybe one can reorganize the physics somehow in this surface language, because there are somehow information barriers. So it's a bit in this direction of trying to reformulate things more in information theoretic terms. So for example, some of these quantum extremal surfaces, they're related to like these Python lunch type phenomena, where you have pieces of space-time that are exponentially hard to reconstruct from the boundary point of view. That again, so those again act as some sort of information barrier, because it's very hard to connect the information from the outside to the information on the inside. So that's why also all these subleading ones in principle are interesting, I think.
Thank you. So there will be much more time for questions during the breaks if people want to approach Jan and discuss. For the moment, let's give him again a big hand. And let's welcome our next speaker, Kostya Zarembo.
Yes, I would like to thank the organizers, first of all, for setting up meeting in this beautiful place and for giving me the opportunity to speak. I'll talk about another instance of holography, ADS-CFT, where we actually do have a hope to solve things exactly and completely. And, well, this is just the basic duality between n=4 super-Yang-Mills and strings of the ADS5 cross S5, which, as we know, is an integrable system. So it manifests itself on the weak coupling side if we interpret the dilatation operator as a quantum spin chain. This quantum spin chain turns out to be integrable, and it can be solved by beta ansatz. On the strong coupling side, the scattering theory on the wall sheet of the string turns out to be integrable, and I mean, its S-matrix satisfies all axioms of integrability. And again, one can apply the machinery of integrable systems to figure out what happens dynamically. And actually, one can bootstrap what happens in the middle at any coupling and understand ADS-CFT at the quantitative level in any coupling regime. And it works beautifully for the spectrum, but it's a general truth about integrable models that it's always possible to understand the spectrum. Whatever integrable system you take, there are some sort of spectral equations that you can write, and it will be beta ansatz or, I don't know, Y system, or there is a very efficient tool specially tailored for ADS-CFT that's known as quantum spectral curve, which describes the spectrum of the theory, which, because it's a CFT, it's this spectrum of scaling dimensions. But if you go to correlation functions, even in simple integrable models like, I don't know, Heisenberg spin chain or one-dimensional Bose gas, it's still very much work in progress how to compute them. the correlation functions are difficult. And also in ADS-CFT, no one, well, there are proposals, but there is no final theory that would compute you any correlation function at any coupling strength. So I'll talk about an instance where actually from general knowledge about integrable models, we expect that such exact description should exist. And this related to D-branes, so, or defects in conformal theory. So you may consider a D-brane placed in the bulk. Well, if it happen to end on the boundary, that would produce some sort of defect in the dual CFT. A D-brane is an endpoint of open strings, and potentially it will break integrability. So even if excitations of the string scattering among themselves elastically, and the rest matrix satisfies all the Young-Baxter equation and so on, the boundary itself may break integrability because the reflection of the boundary may create particles, and the boundary conditions need not necessarily be consistent with integrability. So there are a set of requirements that the boundary conditions should satisfy, and if you are lucky, then the D-brane itself will be integrable, and then one, in principle, can apply usual integrability bootstrap in this setup. So what can we compute then? Well, the ingredients in principle are known. So the basic ingredient of an integrable field theory is an S matrix, and there is a known expression for the S matrix of ADS-CFT that was derived by Bizart many years ago. So the boundary introduces an extra scattering factor because an excitation can reflect off the boundary, and for the integrability to be preserved, this reflection has to be elastic. But it can change quantum numbers, so it is described by a matrix with two indices of incoming and outgoing states. And there is a certain set of consistency condition between the S matrix and the reflection factor. If they are satisfied, then the system will be integrable. But these conditions are typically so strong that you can find that they more or less uniquely fix this matrix and the boundary reflection given the symmetries of the problem. So they can be basically found from integrability bootstrap. So these are the ingredients, but then it is known from studies of integrable quantum field theory that given these ingredients, one can actually compute universally an basic quantity that characterizes a boundary of the string worldsheet, which is just the boundary entropy. And this is defined by the partition function on a half-infinite cylinder, so that, it will have a bulk piece, which is basically given by the ground state energy. So if you think of this direction as time, this would be the usual Boltzmann factor. But then the prefactor will depend on the circumference of the string, and this is known as the G function in statistical quantum field theory. And if a QFT is integrable, then there is a generic well, method or idea how to compute this, this function by through thermodynamic beta ansatz. So if you go to ADS-CFT, then, well, what is the physical meaning of the boundary entropy? So this would be the worldsheet of the string that ends on a D brane, and then the other end of the string should end on the boundary. This is kind of a natural thing for a string to do, that it will approach the boundary at infinity. This other endpoint describes a local operator. So the states of closed strings are dual to local operators in the dual CFT. So this will describe a one-point function of this operator in the presence of the defect. So since defects break conformal symmetry a little bit, we assume that they don't break it completely. So for instance, scale symmetry is still there, but translations in the directions perpendicular to the defect are obviously broken. And then one-point functions are allowed. So they are not zero, and this is the simplest response function that one can imagine in the presence of a defect. And in the integrable situation, this should be proportional to the G function, or just given by the G function of the dual string theory. So generically, the defect will indeed intersect the boundary at, well, at a line or a point or two-dimensional hypersurface and so on. And so in that case, it will describe a defect conformal field theory, where this would be a line defect or a point defect or a surface defect or and so on. So the D-brane can also go parallel to the boundary, and in that case, it describes the situation where the gauge symmetry is Higgs, or it's spontaneously broken. So this corresponds to Yang-Mills theory going onto the Coulomb branch. Or it can end on the boundary at 2 points, and this corresponds to inserting some heavy probe. For instance, it can describe a 3-point function with 2 operators being very heavy and 1 operator being very light. So all of these setups corresponds to D-branes, and they can be studied in some sense in a uniform manner. But as usual in integrability, there is no plug-in formula, so one has to study each case anew. But the techniques are similar, and the architecture of the formulas one gets are also similar. Okay, so in string theory, D-brane, well, it's either a surface on which open strings can end, or you can think of it as a surface which it can absorb closed strings. So in integrability, this is also these two dual descriptions. They are mutually interchangeable, and both are important and convenient to use. So one can either think of this as a theory on a half line, so this time direction now goes in the vertical direction, and space is half infinite, so the worldsheet ends at some point. Or one can view this horizontal direction as time, and then vertical direction as space, and then this would be a worldsheet of a closed string that emerged from a D-brane. And in this case, the D-brane is described by a state, by a particular state in the Hilbert space of the closed string. So the question is how to characterize it from integrability point of view. And this was, there is a well-known paper by Goshal and Zamolodchikov from 30 years ago that sorted out this question in full generality. And basically, the idea is the following. So in this open string picture, the integrability condition requires that reflection of the string modes of the boundary are elastic, so there is no particle production involved in the reflection process. So if there is one particle that approaches the boundary of the string, it can bounce off with the same momentum, and it cannot produce a pair of virtual particles. Well, virtual particles it can produce, but it cannot produce other on-shell modes. And it cannot change the momentum, only the quantum numbers. So if you view this in the cross-channel, then this state at the boundary will consist of pairs. So it will be a coherent superposition of paired particles with opposite momentum. So the state will be, roughly speaking, given by this. So this will be a collection of paired magnons with opposite momenta, with some weights, well, which at this level are not fixed. And so, in this sense, integrable states are those that have this momenta paired. Or sometimes people formulate this as a condition that the state is annihilated by all odd charges of the integrable hierarchy, because odd charges are odd functions of momenta. And so if all momenta are paired, then obviously they are equal to 0. And this is a very strong condition, actually. It's, if you take a random boundary state, it will not satisfy it. It's not very easy to find such states. And interestingly, ADS-CFT produced a huge stock of these states that were not known before. So people studied them in condensed matter context, but then the study of motivated by N=4 and string theory, they produced new sets of new classes of boundary states that were not known. Okay, so in this language, the one-point function is an overlap of a boundary state with a given on-shell state of the string that is dual to some operator at the boundary. So it's characterized by some quantum numbers at the position where this operator is inserted. And the question is how to compute this overlap. So there is a remarkable result in the theory of integral systems that this overlap, and with it the one-point function in the defect CFT, always has a very rigid structure. So it's basically given, well, there is a dependence on x, of course, is fixed by scaling symmetry, but then the dependence on kinematics is encapsulated in what is known as Gadan matrix. This is basically a Jacobian of beta equations. So for integral boundary states, the overlap is always the square root of the Gadan superdeterminant multiplied by some prefactor which has a very simple dependence on moment. And basically, this prefactor is the boundary reflection phase in which the reflection is diagonal. Okay, so how much time do I have? For this not to be too abstract, let me give one example. This is based on recent work with Charlotte Christensen, and it has to do with 't Hooft loops. So 't Hooft loops are it's a typical example of a defect operator that exists in any gauge theory, in particular in N=4 super-Egg Mills, and it is a disordered type defect. So it is not fixed by some operator that you insert in the vacuum, but rather by boundary conditions that you give to the fields in the path integral. So, so basically what it does, it inserts a point like monopole of Dirac type, so it's an abelian monopole, at some particular point in space. So its evolution with time covers a line, so it's a line defect. And then, so this field of the monopole is the boundary condition that is fixed at the origin, so as R is going to 0. Now, in N=4 super-Egg Mills, one may or may not add a scalar, but if one wants to preserve supersymmetry, then one better adds a scalar condensate in addition to this gauge field one. And then this defect will preserve some part of supersymmetry. And also, if you don't add the scalar, it may also be, it will require normalization, so it will not be even conformal. Anyway, so for this supersymmetric defect, it breaks part of conformal symmetry, but not all of it. In particular, dilatations are still a part of the game. So it defines a codimension 3 defect CFT with all the consequences for the operator algebra and for correlation functions that one can constrain using basic CFT tools. So the dual description is a D1 brane in the bulk. So if the 't Hooft line is a straight line, then this will be embedded as ADS2 in ADS3, and it will be a point on the 5 sphere. So the point is characterized by this vector that also defines the scalar condensate. And it was known for a long time that the boundary conditions for the string of this D brane do not break integrability. So we do expect, well, this, strictly speaking, this only tells us that integrability is preserved at strong coupling, but, well, having a good faith, we may expect that this will also be true at weak coupling, at any coupling, essentially. And then we may expect that we will be able to compute exactly the one-point functions using more or less conventional tools of integrable models. So I will tell you how to do it at tree level, but for arbitrary operator. Well, so let me just show you how to do it at tree level. So, so first of all, what are we actually calculating is just a constant, because the dependence on the distance is fixed by scaling symmetry, and this constant can be also viewed as an operator product coefficient of a small 't Hooft line. So if you take, we can always map a line to a circle. And if you view the circle from very far away, then the correlation function, the one-point function, will be determined by, obviously, by the same coefficient. Since, well, there is an extended object somewhere near the origin, and we probe it from far away, this is basically OPE. So the 't Hooft line is expanded in the powers of its size, with the operator coefficients, and this operator coefficient is I think we need some cheer up, no? So this is so these numbers are p coefficients of the circular 't Hooft loop, which we expand in local operators. Then the question is how to calculate them. Well, for protected operators, they can be actually extracted from localization. Here is the formula. I will not tell you how to derive it, but we did it. One can presumably do it very directly by localizing in the presence of the 't Hooft line, but we did it using S-duality, so we can map this problem to a correlator of a Wilson line, for which the answer was known from the work of Akuyama and Semenov and myself. And then, so invert the coupling and take the large N limit, and then we obtain this very compact formula, which is actually exact. So it is non-perturbative in lambda, and if you expand it in the power series in lambda, it has finite radius of convergence as expected from planar perturbation theory, and indeed one can check that the first two terms is just classical contribution, where we replace all the fields by their classical values. And then the first correction is when two of the fields are connected by a propagator. And there is actually a very beautiful theory of how to quantize in the presence of magnetic monopole that goes back to the work of Dirac in the 30s. And so one can use this monopole theory of monopoles to find the propagator in the presence of the 't Hooft line. And indeed, everything works beautifully. This reproduces the localization result. At strong coupling, well, one can get even a simpler answer, and one can reproduce it by integrating now the propagator in ADS, so whose one end is sitting on the boundary, the operator insertion, and the other end is integrated over the D1 brane. So that also reproduces the expected result with all the coefficients. Okay, so but if we want to compute a one-point function of a non-protected operator, then a priori we don't know how to do it, apart from just using Feynman diagrams. But integrability can help, and so in that context, it is convenient to think of operators as spin chains. So for instance, if you consider an operator built of scalars, then this will be characterized by a wave function of an SO6 spin chain, which is integrable, and its spectrum can be computed by beta ansatz. So by solving a system of beta equations with three types of beta roots, because the symmetry group SO6 has rank 3, and the beta equations are completely characterized by the group theory data, by the Cartan matrix, and the highest weight of the spin representation. So solving this equation, we can find all the states and all their one-loop anomalous dimensions just algebraically from the beta equations. Okay, so then if you want to compute the correlator of this operator with the 't Hooft line, at the leading order, we just substitute the fields with their classical values. And in the language of the spin chain, this projects the state, given state characterizing the operator onto a state with particular components at each side. So in a sense, we are just picking one particular component of the wave function where the spins are aligned with the vector that characterizes the 't Hooft line at every side. And so one needs to compute this overlap for a given state. Now, integrability by itself and beta ansatz produces an expression for the wave functions of the states, but they're not really useful. In fact, to compute them, so if you want to put it on mathematically, it's easy to diagonalize the Hamiltonian as a matrix. So the beta ansatz expressions are sums over permutations of lengths that is given by the number of excitations. So they grow very quickly in complexity, and it's just meaningless to use this expression in computing the overlaps. But this state turns out to be integrable. So it does satisfy this selection rule that it only projects into paired states. So if the state is characterized by n magnons, the overlap will be 0 unless these magnons are paired. That for each rapidity we have the state with the opposite, with the rapidity that have an opposite value. So the state must obey this Z2 symmetry. So if it does not, the overlap will be 0. And we know that for these integrable states, the overlap should have a universal form in this determinant representation. So for this particular state, actually this representation was already known. It was derived by Deleuve, Gomberg, Christensen, Leonardopoulos, and Poshgai. But if it were not, it's very easy to just, well, if you know that the answer has this form, guessing this prefactor is super easy. You need to compute an overlap with just one state. Well, so this produces the answer that is valid for any state whatsoever, well, to the one loop accuracy. And presumably there is a generalization of this formula to all loops. What one needs to find is how this prefactor is modified, because the Gadan part stays the same. So one can also do the same game with the operators that contain derivatives. Let me maybe skip this part. So, here one needs to use the formula that was derived by Legendre in 1785. Basically, the boundary state will be linear combinations of Legendre polynomials. So linear combination of all states of the spin chain, and here the Hilbert state at each side is infinite dimensional. So potentially the boundary state can be arbitrarily complex, but what we get is very particular coefficients that are given in terms of Legendre polynomials. And quite remarkably, the integrability condition for this state is basically boils down to the recursion relation for Legendre polynomials. So this state is also integrable, and indeed it has a very simple overlap expression, again in terms of Godin superdeterminant and some prefactor depending on the Q functions of the state. So this was more for an illustration, but there is by now the whole list of defects that turn out to be integrable. And in some cases, the answers are known even non-perturbatively. For instance, for D3, D5, a CFT that describes domain wall between the vacuum with different gauge groups in n equals 4, or for heavy light correlator. There are also some results for domain walls in ABGM theory and for the 't Hooft loops, but so far they are only one loop exact. So there is still some work to do here to find a fully non-perturbative description. So there were very recently there was veritable progress in ADS3 as CFT2 duality related to integrability. To the best of my knowledge, D-branes there have not been discussed, which to me looks a bit surprising because in that case there is an interpolating parameter that brings, so it's basically the amount of the Ramond charge in the background. One can dial it to 0, and then string theory is described by conventional worldsheet CFT, and well, they're studying D-branes as a very classic topic in string theory. On the other hand, integrability is by now is also well understood, so one can apply similar techniques to study also real Ramond backgrounds. Also, for the 't Hooft line, it's very natural to combine integrability with the bootstrap, which was done for the Wilson line so far with great success. And I would expect that for the 't Hooft line, it will also, should also work in parallel because it's a one-dimensional DCFT and one-dimensional CFTs are simpler. There's only one cross ratio, for instance, in the 4-point function. So this would be a natural playground to also extend the bootstrapability approach. So with that, I would like to thank you again, and thank you very much.
Thank you very much, Kostya, for this very nice talk. Are there questions for Kostya? Yes. Oh, there are a couple. Let's do Boris and then Zoli.
Thanks. Just a very short question. So in n equal to 4 super Yang-Mills, just like you need a choice of representation for Wilson loops, there's also a choice of representation for 't Hooft loops, presumably?
Yes.
So
yes,
were you just computing the one-point functions for a 't Hooft loop in the fundamental, or could you generalize?
Yes, yeah, this is the simplest. We were doing the simplest case, which is, so for the, yes, Wilson loop is characterized by, you can say, by Dynkin labels and numbers. And the 't Hooft loop is characterized by n charges of the monopoles in each of the Cartan vectors. So we considered the simplest ones which have only one charge, and it's elementary one allowed by 't Hooft
principal integrability holds for the whole set of them.
Yeah.
So you showed this formula for the overlap which contained the superdeterminant and products of factors in the ADS CFT before. So
Yes.
this is valid only for large operator, no? Or
Indeed, yes.
yes, and can you prove this formula, or why is it a product?
I thought you proved it.
No, actually, recently we analyzed this TOF loop, and we found that it's not always a product form.
Well, there can be linear combination of this type of formula. So this is the building block. This is what you mean?
No, it depends actually on which grading you do the calculation, and in some grading it's a product form, in some other grading it's a more complicated expression.
Aha, that's interesting. You should tell me how.
Yeah. Another question. You mentioned some exact formula for this BPS Wilson loop, and then you showed that there is one piece which is a wrapping correction.
Yes.
So I was a bit wondering, because this is a supersymmetric object, and I would believe that the wrapping should be 0.
Why?
Because fermions and bosonic contributions should kill each other.
No, but this is in the non-trivial vacuum in a sense, right? So the operator itself is BPS, but then you couple it to a D-brane, which is sort of orthogonally. It's also supersymmetric, but the supersymmetries do not completely match. So the one-point function is non-trivial, right? So it's
yes.
a full-fledged function of the 't Hooft coupling, and it contains wrapping and everything. It's the same for D3, D5.
But this is an exact formula what is on the screen. So no more correction, this is exact.
It's large and exact.
Yes. Okay, I will think.
So in view of time, I would say that we can thank Kosti again. And I have a couple of announcements. So first of all, there is going to be a coffee break in a moment. It's a good occasion to continue discussion with the speakers, but also some of the posters are already up. Others, I think the presenters will put them up during the break, so you can start a pre-poster session by chatting with people. It will be 30, 40 minutes, so there will be plenty of time, plenty of food. A couple of unforeseen announcements. First of all, those of you that registered to the guided tour of this palace, it has been cancelled because of essentially the demonstrations. However, you can enjoy this beautiful room, which is the Aula Magna. That old thing that you saw just outside is actually the podium from which Galileo himself was lecturing in that room, which is called the Sala dei 40, the room of the 40s, because there are 40 portraits. And over there is a room which is called La Basilica, which has very nice frescoes. And if you take the opportunity to go to the restroom, you will go through another very beautiful room, which is the Archivio Antico. So you can, walk a little bit around. That's the first thing. The second thing is that I will have to disappear. I hope to be back soon to discuss a little bit with the rector whether the current situation allows us to stay here. It's perfectly all right for us to stay here, but it's very difficult, for instance, to bring the food up for the catering, and we are supposed to have lunch here. So we have to sort out some practicalities. We'll continue here until lunchtime, and then we have to figure out essentially how to get some nice food. But other than that, just enjoy the coffee break and see you in a little while.
All right, thank you for coming back to this second half of the morning session. So I'm Fiona Seibold, I will be chairing this session, and we're very happy to have Lorenzo Di Pietro, who will tell us about taming the mass gap with anti-de Sitter space, please.
Thank you. Can you hear me? Yes. So first of all, let me thank the organizers and Alessandro in particular for putting together this very nice meeting and inviting me to speak. So this is the title of my talk, and so in order to try to fulfill the spirit of a vision talk, I decided to start with some very general motivations, so it will not be immediately clear what my title is about. So how does it work, the pointer? Maybe. But okay, hopefully it will become clear as we go. So my seminar is about an approach to quantum field theory. So let's start from there. So quantum field theory is our framework that puts together quantum mechanics and locality. And as we all know, it's very successful. And we know that it's very successful because we have a very well understood method to obtain predictions, which is the use of perturbation theory. And this relies, of course, on the existence of some small coupling constant that we use to expand observables. However, I mean, even though in some cases we know how to do this, it's fair to say that in general it's still an open problem to understand how to compute observables in the regime of strong coupling, where our interaction strength is of order 1. And this is not something that it's easy to avoid. One reason to understand this is from the point of view of the renormalization group flow, of which I drew a cartoon here. So even though we might start with some microscopic description at small scales, which is weakly coupled, one thing that we learn in quantum field theory is that the coupling constant in general is a function of the length scale. And so as we increase our length scale, we might go to the regime of strong coupling. And so in this framework, the question becomes, if I give you some microscopic description, how are you going to go about computing predictions for the macroscopic observables? So in particular, a question that one encounters often is very hard to answer is, if I give you some microscopic description, can you tell me if there is going to be a mass gap above the ground state? So that's a very hard question. And OK, so this is the case of massive quantum field theory. But then there is a special case, which is a little bit more tame, which is the case of conformal field theories. So conformal field theories are a special case of QFT in which we don't have any mass scale, and so we have a larger symmetry group. They are useful, for instance, to describe the limiting case of mass in quantum field theory, so in the limit of very small or very large scales. So they are sometimes called signposts in the space of quantum field theory. And in this case, it's sometimes possible to make progress even at strong coupling, using only consistency conditions and symmetry. And this is what has happened in the last 15 years, for instance, in the program of the conformal bootstrap. So a very natural thing that one might hope is, OK, can we build on this progress to somehow also use it for massive quantum field theories? Of course, there is not a single way to try to do this. One way one might try is, for instance, to use this picture. You know, if we know how to solve the theories that live at this signpost, then we can try to deform. But that's not what I want to do, what I want to talk about today. So another possibility, the one I will talk about, is to use anti-de Sitter space as a background for quantum field theory. So I want to argue that somehow it's a bridge between the two worlds of massive and conformal quantum field theories. Okay, so this is the metric of idea space, Euclidean, and the cartoon on the right. And as we know, this is a maximally symmetric space with negative curvature. And the symmetry of this background is the same as the conformal group in one lower dimension. as we all very familiar with from ADS-CFT. If we study a quantum field theory in this background, then we can ask what is the analog of scattering amplitudes. And the analog of scattering amplitudes are correlation functions of local operators that are inserted at boundary points. Okay, so I'm free to study this subset of observables. And this is a very rich subset of observables because it satisfies the conformal symmetry thanks to the symmetry of the background. And so what we discover is that in any massive quantum field theory, once we place it on this background, we have a very rich subsector which forms a conformal field theory living on the boundary. So that's the kind of connection that we talk about today. So summarizing this introduction, this seminar is about studying quantum field theory, rigid quantum field theory in an anti-de Sitter background. And let me list, besides what I already said, some reasons why I think this is nice. So we saw at the beginning that one of the problems in studying quantum field theory is that sometimes we have very large fluctuations at large distances, which make the theory hard. And ADS also behaves, in a sense, like a box. So it provides us with some IR regulator. It is an IR regulator which has a lot of symmetries. So in that sense, it's much better than putting your quantum field theory in a box. And so another nice thing of having a radius is that you can use it to probe the theory at different scales. And on the other hand, okay, so far, I mean, an IR regulator with symmetries could also be a sphere. I could put my theory on a sphere. But there are a few points why ADS, I think, is better than a sphere. So first of all, it has an infinite volume. Even though it has this property of being like a box, actually the volume is infinite. So this means that you don't have to give up on many interesting field theory phenomena, such as symmetry breaking or phase transitions. And what I said already in the previous slide, unlike a sphere, we have this very rich set of asymptotic observables, which are the correlation functions of local operators inserted on the boundary, which form this boundary conformal field theory. Okay, so this is the setup, the general setup. Now let me try to go towards my title. So let's specify a little bit and say what we want to do. So the setup that I want to consider in this general framework is the case of dimensional transmutation for a field theory in anti-de Sitter. So I want to consider the case in which our microscopic description is some UV classical theory which has massless degrees of freedom that are weakly interacting. Okay? And then, as it often happens, however, in the IR, the theory develops a mass gap. So schematically here I wrote it in the form of a dynamically generated scale. And so if we now vary the radius of ADS, so it's like varying the size of our box, we can interpolate between these two regimes. Okay? So we have massless degrees of freedom when ADS is small, and then we should see this mass gap when ADS is large. And at least in some cases, one can argue that actually there should be a sharp transition between these two regimes, which, as a result, should be detectable from the point of view of the CFT living on the boundary. So this gives us what I think is a very nice opportunity, which is the opportunity of studying the boundary conformal field theory as a way to detect, or perhaps optimistically even try to prove the existence of the mass gap in the bulk. Okay, so that's the goal. So now that's the outline of the more technical rest of my talk. So first, I will give a brief review of the example that inspires this story, which is the example of Yang-Mills in four-dimensional anti-de Sitter space that was studied in this very nice paper some 10 years ago, or a bit more. And then I will mention my work in which, with Christian Kopetti, Zimiji Shotakomatsu, in which we studied two-dimensional examples, so simpler toy models of this. In particular, we looked at ON sigma models and ON Grosneve model, okay? And in this setup, what we could use is an additional computational handle, which is the large N expansion. And okay, it's worth mentioning that all the foundational papers on large N expansion in quantum field theory came out 50 years ago, so we should celebrate. And so let me start now with the Yang-Mills in ADS4. So again, what we're going to do is that we're going to vary the size of our ADS, which here I depicted as the disk. And as we cross the scale set by the dynamically generated scale, we are going to argue that there is a transition. So let's start here on this end. So on this end, perturbation theory is reliable. And so we can reliably look at our Lagrangian and decide what to do. So if you look at our Lagrangian, one thing that we can do is that we can impose Dirichlet boundary conditions on the gauge fields, meaning that we take our non-abelian gauge field and we say that it behaves in a certain way near the boundary. And in particular, it defines this operator J mu A, which from the equation of motion, we see that is a conserved current. Okay? So far, this is a very usual story to anybody who studied ADS-CFT. I'm just saying that with this boundary condition, a bulk gauge symmetry gives a global symmetry on the boundary. On the other hand, we think we also know something about what happens when ADS is very large, right? Because ADS is very large means that we're basically in flat space. So when we are in flat space, we expect that there should be no colored asymptotic state, and there should be a mass gap, right? So the mass gap, once we are in ADS, talks to the dimensions of operators that we see in this boundary CFT. So all the dimensions should scale like the length of the ADS if we have a mass gap. So in particular, all the dimensions of boundary operators should be much greater than 1 in this limit. In particular, this current, so if a conserved current doesn't have a parametrically large dimension, it has protected dimension, so somehow in this limit, this current must have disappeared. And we can argue precisely that this should be a sharp transition. It cannot be a continuous change. And the reason why it should be a sharp transition is because when we are in the perturbative regime, we can check. So what is the perturbative regime? It's just a mean field theory, sometimes also called generalized free theory of this operator, which is a current. And then we have small corrections to it. And you see, there is no candidate operator we can build here that can possibly appear on the right-hand side of the conservation equation. Because you see, if an operator appears here, it must have dimension 3 and be a scalar operator in the adjoint representation, and just there is no candidate in the free theory. So since there is no candidate, there must be a continuous range of L such that the theory keeps having the conserved current, okay? And so there should be a sharp transition at some critical length, which we expect to be of order of the dynamically generated scale. Okay? Now, what are the possibilities for these transitions? One can imagine various scenarios. So one possibility is that perhaps there is some bulk charged scalar that condenses. So in each of these, we can have both the point of view of the bulk or the point of view of what we would see from the boundary CFT. So in the boundary CFT, this would mean that there is some adjoint scalar operator, which becomes like hits dimension 3, and then recombines with the current. So it can appear. Now we have something that can appear on the right-hand side, and so this makes our current lift from the spectrum. Another possibility is that somehow the gluon states decouple at some point. So this would mean that from the point of view of the boundary CFT, you see the two-point function of the current is what controls the norm of the gluon state. And so it could be that this coefficient Cj which is a boundary CFT observable, perhaps continuously go to 0 at some critical value, and then the gluons disappear. That's another possibility. Or another thing we can imagine is that maybe the boundary condition becomes unstable because there is some weakly coupled scalar that somehow emerges from as a bound state of gluons, and this weakly coupled scalar gets a mass which is below the Bertalanffy bound. Okay, so that's another possibility, and it has also some explanation from the point of view of the BCFT. Let me not get into that. Now, what we did in our work is that we looked at these 2D toy models, and motivated by what happens in these 2D toy models, we actually proposed a generalization of this scenario 3, because you see, one little shortcoming of this scenario 3 is that somehow, in order to be talking about a scalar that goes below the Bertalanffy bound, I need to rely on some weak coupling intuition, right? Because I have this scalar that has negative mass squared. But this can be phrased more generally, without relying on any weak coupling idea, by saying that what we call marginality. So it could be that at some point, a singlet scalar operator hits dimension 3, okay? So what happens in this case is that you see this is a singlet, so you're forced, when it becomes marginal, you're forced to add it to your Lagrangian, and you should ask yourself the question, what is the beta function of this guy, okay? And you can prove in general that if on one side, let's say, you could satisfy the constraint that the beta function of this coupling is 0, and you found that you have a allowed conformal boundary condition, then as you increase the coupling past the point where delta became 3, actually you cannot satisfy anymore the beta function, okay? You cannot satisfy anymore the beta function, and okay, this is can be described in the language of merger and annihilation. So the boundary condition that you had before disappears. Okay, so this is what I think is the most likely scenario. So I think this is a nice story, and perhaps suggests that one could try to set up a bootstrap approach to the mass gap in Yang-Mills. So what we described is that once we put Yang-Mills in ADS4, automatically we get a family of CFT trees. So non-local just means that since I don't have gravity in the bulk, then the CFT trees don't have a stress tensor. But for the rest, they are exactly the same as any CFT. That have a global symmetry, which is exactly the gauge group. And then this continuous family is parametrized. For instance, you can parameterize it using the value of Cj, which is in correspondence with the bulk coupling at the ADS scale. And then we know that when Cj is very large, we approach the mean field theory. We can compute perturbation theory, for instance, and some people already obtained some of the CFT data at order 1 over Cj. But the goal is really to try to go beyond perturbation theory and try to see that at some point this boundary condition must disappear, okay? So can we somehow prove that this boundary condition, the Dirichlet boundary condition, cannot exist at arbitrarily small Cj? That would be, I think, like a long way towards, in a sense, proving the existence of the mass gap in Yang-Mills. Probably to not be accepted by the Clay Mathematical Institute, but still. So now, in the case of ADS4, this transition that we described is a confinement transition. So now I told you that what motivated me to look at this marginality condition were actually 2D examples, which I will now plan to discuss. So first I need to tell you what is an analog of this confinement-deconfinement transition in the case of ADS2. How am I doing with time? 7 minutes. Okay. So the analogous phenomenon that we studied is what could be called a Goldstone gap transition. So what we did is we considered bulk theories which have a continuous global symmetry. So this time the global symmetry is in the bulk, okay? And when I am in the regime of perturbation theory, I can impose a boundary condition that breaks this symmetry. So this is just a boundary condition in which the normal component of the current is not 0 at the boundary. And this operator TA, which appears as the normal component of the current at the boundary, it's actually protected in the boundary CFT. It's always of the same dimension as the boundary dimension. So it's a marginal operator. So what happens is that every time you impose this boundary condition, you actually have a continuous family of boundary CFTs. It's kind of an analog in ADS of the Goldstone theorem, right? This family of CFTs, you should think about it as the same as having a manifold of vacua parameterized by your Goldstone boson. So this boundary condition is like spontaneously breaking a symmetry in ADS. On the other hand, if we are in two dimensions, we know that when L is large, Goldstone boson should not be there. So again, there should be a transition in between. So the objective, what we did in our paper is that we try to understand very well this transition in two-dimensional examples that are under control thanks to large N. And OK, so now I will not give a lot of details, but we did this, for instance, for the ON model in ADS. And this is the model of just N scalar fields with a constraint. And at large N, the usual trick to solve it is to introduce this Hubbard-Stratonovich auxiliary field. So the first thing you do is that you expand around some VEV, and you look for the gap equations, for the vacuum equations. And okay, let me go fast over this. Like, the surprise is that in flat space, of course, you find that there is no symmetry breaking in two dimensions. Well, in ADS, you find that there is a regime of lengths when length is sufficiently small for which symmetry breaking can happen. So this is the picture. So you have the length of ADS. When length is small, you have symmetry breaking. And then for large length, you have a gapped phase. And then, OK, so far I just told you that you do this analysis of the bulk gap equations. So now you can ask me, how do you see this transition from the point of view of the boundary CFT? So that's what we set up to answer. And in order to do that, we just looked at the spectrum of, so we started from this phase, which is very well understood because it's weakly coupled. We just have our Goldstone bosons. And then we looked at the spectrum of ON-1 singlet operators. And what we observed is that as we go towards the transition, one of the operators hits marginality. A singlet operator hits marginality, and that's what destabilizes in the way I described before. So there is a merger and annihilation. OK, let me skip this. This is the details of how we computed the spectrum. But this is the picture. You see, we have these black lines are the spectrum of operators in this weakly coupled boundary condition with symmetry breaking. So what you see is that as you increase L, at some point, the lowest operator hits dimension 1. And that's precisely when so the boundary condition disappears, and you're forced to go to the new boundary condition. It turns out that the correct boundary condition you end up in is still a Dirichlet kind of boundary condition, but which preserves the ON symmetry. I guess now. 3 minutes. OK. So yeah, that's the picture. At this transition point, an operator becomes marginal. And if we try to push the symmetry breaking boundary condition further, you actually discover that it becomes complex. Some observable in the spectrum become complex, so it's not acceptable anymore as a unitary conformal boundary condition. And so this is the picture that, like our manifold of vacua, continuously shrinks, and then we flow to the symmetry preserving phase. But the important point is that we managed to detect this from the point of view of the boundary CFT. Okay? So we have a condition which is purely in terms of boundary CFT. Okay, so let me summarize. So I discussed transitions from gapless to gapped phases in ADS. And the focus of my work has been on solvable examples in 2D, which point towards, so what we gain from them is that they point towards one particular mechanism for the disappearance of the gapless phases, which is the mechanism of merger and annihilation. And I think there are several interesting future directions. So One clear thing to do, it was already mentioned in previous seminars that 1D CFTs are supposed to be easy. So one thing we should try to do is to try to actually bootstrap the boundary conditions for these ON sigma models and also for Gros-Neve. I didn't have time to discuss Gros-Neve, but the story is very similar. And actually using numerical conformal bootstrap, I would like to try to actually prove this transition to the gapped phase even at small n. I think there is still a role to be played by solvable examples in this context to gain more intuition about what happens. And one solvable example that doesn't rely on large n, but instead relies on supersymmetry that I'm looking at is the one of n equals to Super-Yang-Mills in ADS4. Also there should be a transition between non-abelian Coulomb phase when ADS is small to some Coulomb phase when ADS becomes large. A bit of a mystery is, I told you that there is this merger of annihilation, but there is a mystery of what is this Dirichlet prime, we might call it, boundary condition that merges with the Dirichlet boundary condition in Yang-Mills and makes it disappear. So for instance, one definite question is whether this boundary condition also exists in the regime of weak coupling or whether it comes in some weird trajectory from strong coupling. This we don't know. And also a very concrete thing that I'm also looking at with some students and collaborators is that we definitely should compute more perturbative data for Yang-Mills in ADS4. Okay, thank you.
Thank you very much, Lorenzo. Are there any questions?
Thanks for the nice talk. So something that is not clear to me is that, okay, you start with Yang-Mills in ADS, and then you say, okay, there is a BCFT describing that. But is it obvious that this would-be CFT satisfies all the axioms of, all the bootstrap axioms of CFT?
Well, I think the only thing that it doesn't satisfy is the existence of the stress tensor, as I mentioned. But for the rest, yes, I mean, you can build all the charges acting on local operators, and the boundary correlation functions will satisfy crossing symmetry. So,
okay, they do satisfy crossing symmetry. But
well, maybe one thing that you have in mind is that sometimes you might want to define local operator insertion with some lines attached. But here I'm talking about genuine local operators on the boundary. The infinitely many of them must exist, and they satisfy the usual axioms of correlation functions in a conformal field theory.
But if you do, for example, block decompositions, maybe you see more operators than what you would want to. I don't know.
There exists a convergent boundary operator product expansion. It's very similar to the case of boundary CFT in that sense. Of course, what you don't have is the bulk OPE, if the theory is massive in the bulk. But you can easily prove that there is a convergent boundary operator product expansion, which is like the boundary operators appear there, and you can build them in this way, like pushing bulk operators close to the boundary. You create some. You can see what is the spectrum of boundary operators.
Okay, thank you.
No problem.
All right. Yes.
So I suppose that Coleman-Merman-Wagner theorem doesn't apply to ADS2.
Exactly, it doesn't. So that's exactly the point that, you see, we have a full range of lengths in which there is spontaneous symmetry breaking. But of course, at some point, Coleman-Mermin-Wagner must kick in. And so this is precisely this transition, that when you try to make ADS large, at some point you must have a transition towards the gapped phase.
So the infrared divergence is therefore not that severe as in flat space?
Exactly, exactly. So this, you can see it from the effective potential, if you want, when you study the gap equation. You see, when you do the gap equation in flat space, the behavior when the Bebo-Deibler-Satanovich field is small is this divergence. So this divergence is responsible for the fact that you don't have spontaneous symmetry breaking solutions. But if you do it in ADS, the log of sigma gets replaced by a log of L, and so you have spontaneous symmetry breaking solutions.
So what you would expect at finite n, like in the
Yeah, I mean, it's not like I have a lot to support my belief, but I do think that something similar should work also at finite n. And I think there is a strategy to do this, which is to do bootstrapping the conformal field theory on the boundary. This can be done also for small n.
So imagine if I would start doing calculation in your theory for small radius of ds. So you get some perturbative expansion, you some moment you have this coupling constant running, you have domain equal scale appearing. On the other hand side, you're going to have some non-perturbative corrections also.
Yes.
Contributing. Those non-perturbative corrections will have dependence on n. Do I understand correctly that in large n limits they will be dying?
You're saying that I might be worried that at large n I suppress some non-perturbative corrections?
Yes.
And then the picture might be dramatically different at small n.
One thing which will change, which I'm certain about, that your argument about phase transition was based on the collision of two different operators.
Yes.
And this collision will never happen for finite n. The fact that you have a collision is an artifact of going to large n limit.
No, but sorry, the collision was not, perhaps you have in mind that I have two operators of different dimension that become of the same dimension. No, that's not what I meant. What I meant is that one operator, just one, becomes marginal. So one operator hits dimension, which is the same as the dimension of space-time. That can happen, right? I'm not saying that two levels match, cross. I'm just saying that one operator becomes marginal. So that happens all the time, even in finite n CFTs. And if this happens, then you have an argument that the beta function for this guy cannot be satisfied on the other side. So that's why there is a merger and annihilation, but there are two CFTs that merge, not two energy levels.
But this picture which you had at the very end, you have these different branches of these functions. One,
you mean this one?
This one.
Right, but you see...
I'm talking about upper one, yeah.
Yeah. But this happens, okay, so maybe the continuity here is a bit strange, the continuity of the transition. But you see, precisely from the fact that this picture is continuous, you see, the manifold of Vacua shrinks to 0 size, and then you start getting a mass. So there is a transition, but it's a continuous one. So it must somehow happen that this second operator must become some other operator after the CFT stops existing.
I'm claiming, if you go to large, this happens because you went to large unlimit.
Okay.
If you include one corrections, you will never have this happening.
Okay, so it could be that what you're saying, I think, is that this continuity here will not happen anymore. Okay, that's possible.
All right. I think in view of time, maybe we can postpone further questions to further discussions. And let's thank Lorenzo again for the nice talk.
Hello again. First of all, a little bit of housekeeping. I was discussing with the rector the situation of this place, and the current situation is that we should leave after the end of our morning session. So I will come with more instructions and the details on it a little bit later after my presentation. But the long and short of it is that we are going to have the talk here, and then we have a little bit of time to discuss and to gather our things, and then we are going to walk all together to the Botanical Garden, which is a very beautiful place, actually. It's not far from here, where we will continue with our afternoon session. And in fact, we will also take our drinks and meal and so on over there. And also the talk by Stanislav Smirnov will take place in the Botanical Garden, and people will be given notice, all the people that wanted to attend it, from the public and from the students. The one thing that is a little bit disappointing is that for a number of reasons that if you're interested I can go into in a little while, it won't be possible to have the poster session there. Unfortunately, it's too complicated to move the posters from here to there. So the poster session will not take place. We will have just some essentially meet and greet session during the upper. We can talk. Unfortunately, we won't be able to see the posters today. We will be able to see them tomorrow and on Wednesday, of course. So they will be up. There will be space for them to be visible tomorrow and on Wednesday. So my apologies to the people that presented, the prepared and wanted to present their posters. Okay, that being said, I would like to start with my presentation, and it is at this point that I realized that I didn't take the remote. So, the idea of this is not a scientific talk, as you see. It's more of a presentation of our action. So what is this action that brought us all here? How does it work? What can you get from it? So let me just give you some of this information. First of all, what is COST? COST is a European network, a European institution that wants to promote among its member countries scientific cooperation and collaboration. And you see that even if it is based around the European Union, it is actually much wider than that. So you can see that there are several countries that are in either purple or green. These are all COST member countries. There are 41 of them. And then there is one, Israel, in orange, which is a cooperating member and has slightly different status. In practice, the big distinction is between the countries in purple and the one in green, because COST finds it particularly important to promote science in the countries that are marked in green, which are called inclusiveness target countries, that according to some metrics have a little bit more to gain from being included into international and transsectorial activities. So our action, theory challenges or fundamental challenges in theoretical physics, is based on the idea that there are many cases in the theoretical physics and there are many cases in physics in general where we cannot just use approximations. We want to have a little bit of more of a handle, techniques that allow us to make more precise statements that don't rely on numerical simulation, and we need more insight, such as symmetries, such as consistency, so bootstrap principles, and some of the ideas that you have heard already in the talks today, dualities, of course. So that's what is the common theme, try to use these ideas in order to go a little bit further than we could otherwise. There is a document, which is the Memorandum of Understanding, that is uploaded to the website of the action, and you can look it up, and it has all the details of what we plan to do, how we want to set up the action divided among different topics. But very broadly speaking, we have set it up in 3 main avenues that, of course, are not completely separate one from the other. One is gauge theories, the other is gravity and holography, and of course there is a clear connection, and the other is low-dimensional systems, because of course there is sometimes a bit more mileage working in low-dimensional systems that you can extract from a theory. So these working groups are where you, as a member of the action, manifest your interest in participating. So you say, I would like to join working group 1 and 2, perhaps, or maybe all of them, or maybe only one. These are the ones that sort of set up our scientific activity. They give the scientific line of our action. The way that the action is run, and this is how COST works, that might not be familiar to all of you, is that there is a management committee. The management committee is comprised by scientists who are appointed by their governments. This usually is typically through maybe your National Science Foundation or something like that. Usually it could be the Ministry of Education. For instance, in Italy, it's the Ministry of Education and Research that does this, but sometimes this is delegated from the government to some agency. And this committee is quite big because it comprises all the countries that are represented in the action, and it votes by country. Because it's very big and because it is a little bit tricky to have discussion at this very large level, there is a smaller committee that is in charge of the day-to-day running of the action, which is the core group. And I will say some words about it in just a moment. In principle, of course, it's the management committee that decides on everything. So the decision power rests really with the management committee, unless, of course, it delegates it. And of course, there are many MC members here in the room today. So this is general. Let's come to our activities, what we can do with this action. So the activities that typically cost actions such as ours have are the organization of meetings, such as this meeting, or smaller workshops targeted to one particular topic, or maybe to one particular region. So for instance, a regional meeting in one part of Europe, or schools. On top of that, there are other instruments that are short-term scientific missions. This means the point-to-point travel of researchers that want to go from their institution to another institution for a certain period of time to do research. And finally, there are conference grants for researchers in these ITCs, the green countries from before, to attend conferences. So this is specific because of cost rules. Is specifically for researchers that are affiliated in ITC. In our case, we have set up a number of these events. The very first event for our action was Iberian Strings, and many of you know that this is a conference that has existed for a while. And of course, what we did here was to co-organize it. The conference was going to take place anyway, but we helped out by giving a little bit of support, which allowed to support more young participants and to make the conference even more inclusive. So this is one way in which we support meetings. Another meeting that was already set up was a school on topology in quantum field theory and quantum mechanics, which took place just in April in Maynooth with about 60 people attending. That was also an event that had been planned before. And then there are events that were not really supposed to take place, but we created ad hoc for the action. And the most important one is, of course, this general meeting, as well as smaller workshop this summer in southern Italy. And then there are some events where it sometimes happens that people that have in mind something contact us, and one of these events is a workshop on black holes and information theory, which is due to take place in September in Belgrade. So this last event was actually not part of our lineup, but it so happens that we had a little bit more money, and the organizer contacted us, so we are planning to propose to the management committee to add this event to our lineup. You see there that it says pending management committee approval, precisely because it's something that I think it's a good idea, and the core group thinks it's a good idea. We discuss it informally, but needs to be approved through some formal process. And I think that this is a bit representative of what one could expect in every given year. To give you an idea, our budget is around 120,000 euros per year, but sometimes we get a little bit of a top-up. This year we go up to 160, roughly speaking. And this allows to support more or less all these activities to a varying extent. Some activities, some meetings that are small get maybe 5,000, 8,000 euros. This general meeting is much more expensive than that. The short-term scientific missions are also something that our community really likes. We have really had a lot of requests for that. They are basically scientific trips of 1 to 4 weeks with a budget of up to 4,000 euros for researchers that want to go and collaborate with somebody else from a coast country to a coast country in the way that we have set it up. And our first call had a budget of 30,000 euros, which sounded like a lot at the time, but we actually got requests for 90,000. And in fact, we managed to fund more or less half of the people by reducing a little bit the amounts that we were giving out. So it was a very big success, and we plan to have another call this autumn as soon as we know the new budget for the new budget year. And the new instrument that was not part of our original plan, but comes because we have a little bit more money, is this possibility to support the young researcher from ITCs that want to go and present their research in an high-profile conference, such as, for instance, could be Eurostrings that will take place in Southampton in September, or some other meeting that is relevant to the community, and there's a lot of visibility for these researchers. This is also something new that has to be approved by the management committee, but is something that in principle can be done by cost actions and can be very useful. So what is all this to you? How does it affect you, or how can it affect you? Well, what you can do is certainly to attend events organized by the Action. Maybe you just attend them. Maybe you also ask for financial support. Of course, financial support is limited. The funds are always limited, but we typically have a call for financial support to which people can apply. You can participate in call for grants, for instance, short-term scientific missions. These are all widely advertised through the mailing list of the Action. So you can get this type of support by being a member of the Action and participating in the calls. But you can do more. You can say that you are planning to have a school, to have a meeting, to have a workshop, and you would like to turn it into a meeting of this cost action. That, of course, means something. It means that it's not just your meeting anymore. It means that the cost action gets involved scientifically in the planning of the meeting. In particular, we really care about not only having excellent science, but also being representative in terms of geographical diversity, age, and gender. So in the selection of speaker or in the awarding of funds, we keep an eye on all these things, and we try to make sure that the meeting fits scientifically with the themes of the Action. Another thing that you can do is that you can join the core group. So sometimes there can be an opening, for instance, to participate in this body that leads the Action, because we find that maybe we need somebody to help out with one particular task. And then we just make a public call for nominations or self-nominations, and you can express your interest, or maybe nominate somebody else. This is something very informal. People that want to join the core group can propose, for instance, I would like to participate in the life of the Action. I think I would be good at doing this thing because maybe you need somebody for this. I make a silly example. We don't have anybody that does social media, that posts on social media what we do, because it just so happens that with the people that are involved in the Action maybe are not so active on this side or don't have that much time. So if somebody says, I would really love to do that, they can come to us, and then what we would do would be to discuss it if we think it's a good idea, and discuss it with the management committee, and then open a call for nominations, and then the person would have to be appointed by the management committee. You can, of course, also join the management committee, but that is a bit of a different process. You need to be nominated by the institution from your government that is responsible. Whether this is simple or not depends on the government. In some places, you just send an email and say, I would really like to do it. I talk to the people of the Action, they think I'm a good fit, and they will do it. In other places, you have to send a CV, and it goes through some committees. Of course, most of the countries already have a representative on the management committee, but not all of them do. Some of them have only one and not two. So these are all ways in which you can join the Action or participate in the Action. In practice, there are some relevant people, and I will ask them to just stand up and come here so we can see them, the ones that are in the room at least. So for the scientific activities, there are leaders and co-leaders for the working groups. For gauge theories, we have Diego Rodriguez Gomez and Predrag Dominis Prester. For gravity and holography, we have Nick Tumbas and Martin Sederval, who is not here. Martin. And for low-dimensional system, we have Riccardo Borsato and Niels Karkvil. So these are the people today, during the meeting, tomorrow, during the dinner. You can talk to them, you can discuss ideas, proposal, ask for clarifications, whether some particular scientific line would fit in the activities, so you can just talk to them. And then there are more colleagues that are in charge of specific aspects within the Action. So I, as chair, sort of try to keep an eye on everything, but I don't really get involved on specific decisions. I try to let other people help out because there is a lot of work. Piotr Sulkowski is also a great help in this. He's the vice chair. He's not here today, but he will be here tomorrow. And then for specific tasks, and again, I would ask them to come here and show themselves. We have, for instance, Boris Piolin, who is the coordinator for grant awarding, so the whole process of awarding grants for instance, short-term scientific missions. Fiona Seibold, who is in charge of communication. Sibyl Driesen, who is our coordinator for sustainability. Nihal Buyutsi-Mechi for inclusiveness. For training and school, we have Saskia, who did a lot of work for the last school in Maynooth. And then I think Paolo Rossi is not, he made it. I didn't see you. Is our coordinator for cross-disciplinary activities, being a physicist by training, but a mathematician by day job, let's say. So these are other people that you can talk to, with whom you can discuss your ideas, specific things, how you think you can contribute to one particular area of their expertise. And finally, I wanted to point out that these networks, they are very good for the community in and of themselves, but they can also be used as an incubator for other networks, other ideas that don't necessarily need to involve all the people of the network, but people that may be within one working group or within one regional area, things like joint degrees programs or doctoral networks that can be also supported through funding instruments of, for instance, Marie Curie. And I think that some people from the Padova offices should be here, so if they are, I would ask also them to come. Alessandra and is it Ilaria that came? Yes. Please come here to the front. So they, of course, are employees of Padova University, so they are particularly involved into activities that involve our university. But if you have just curiosities and you want to know what are the possibilities, what are the calls, what can we do, you can just chat a little bit with them, and they will be able to give you some ideas, some information, at least at the basic level. And of course, if you want to set up something, then if the thing involves Padova, they will be very happy to help. If it doesn't, of course, there will be offices in your own university that can help in a similar way. But it's just to get these also started. So this is all the information that I wanted to give you. And I would really open the floor a little bit to questions, after which I will go back to the practicalities, but maybe if there are questions or curiosity, let's just hear some. Thank you. Any questions on future activities or things that you want to propose? All right, since I don't see any questions on this, let me talk you a little bit through what is going to happen in the next hour or so. So now we have a bit of time just to chat. You can, for instance, chat a little bit with the people that I just indicated if you have questions for them, or you can just follow up with some questions with the speakers of the day. But we will not have lunch here. In fact, the catering services have left because they are relocating to the new venue, which is this botanical garden. Therefore, right now, basically, we have a little bit of time to chat. I asked them to leave whatever snacks were left over. You can have a little bit of a snack if you want, and you can have a chat with the poster presenters. But it is very important that in a little while we wrap everything up, because by 1:40 we have to have everything packed, all your belongings. If you have a poster tube, the poster you detach it, you put it in your tube or whatever, you wrap it up. If you had some luggage that you left over there, you take it, and we meet here in the other room where we had the coffee break. At that time, sharp, because between 1:40 and 1:45, we will be leaving this building as a single group. And that's very important, because at that time, security will be in place to let us leave the building, okay? At which point, after we leave, we can just go. So the security is not really that much for us, it's just to avoid people getting in while we leave. So that really is the issue. So once we leave, as a group, we will walk 15 minutes, more or less, to the botanical garden. You should have received an email, or you will receive it very shortly, from our conference secretary, with a Google map to the botanical garden and indication on how to get there. It's close to the Santo Basilica. You can basically walk out of here and follow the tram line, and you more or less get there, but the simplest thing is stick with the group, okay? We all walk together there. Then, because all this exercise will waste some time, we will continue with the talks when we get there. There are a couple of talks, and then we will combine our lunch and our apéro in some scrumptious meal with drinks that will leave us completely drunk for Stas' talk, okay? So this is more or less the plan. You can take your time now. You can also, have a look around here, the building, to take in these nice places, talk to people, relax, get some snacks now. But it's very, very important that you are there with your things and wearing your badge at 1:40 in order to leave. And it's important that you wear your badge. If you didn't get your badge, it is over there. If you don't find it, come talk to me, because we need to know who you are in order to let you in and out of buildings. Today, it is like this. We roll with the punches, okay? Questions? Yes? Right. There was supposed to be a group picture. So we have the time. So my suggestion is, why don't we take it now, okay? I think that what I would do, other questions before that, because then I will also let the service people able to leave, because after that there will also be, like all sorts of issues. They also need to get there. Puoi lasciare sulla slide quando andate via o devi spegnere tutto? Okay, then other questions, practical questions? Is it clear? Okay, we all get here now and we take the picture here in front.